Great, thank you. Great, then, yes, sir, as ever, thank you very much for the organisers, for the opportunities to speak here in a very enjoyable conference so far. So what I'm talking about today is an old piece of work, and I'll come to the history in a moment. But just before getting into the history, I want to say that to give an idea of what the result is, start with the maths, not quite front load the history, which is that it's about, from one point of view, the existence property for logics, which is a nice property that one can want constructive systems especially to have, which is the desirable property that when your logical system or a theory in your logical system proves that there exists something with some property, then it should be able to construct something with that property. If you're in first order logic, that means it should have a definable witness. If you're in a type theory, it may often mean it should be able to write down a term or something, witnessing the property. And then this categorically corresponds in the, if you've got a logical system that has a good correspondence with categories of some form, then in the classifying category of your logic, this corresponds to the terminal object being projective. So any cover of the terminal object splitting. So that's where we before had the formula, some property, saying that proving that there exists something of it is saying that the map to the terminal object is a cover, and then saying that there's a definable witness is saying that in the classifying category there's a morphism splitting this. And this is something which a lot of good intuitionist systems do satisfy it. It's a funny property in a way because holding in the closed contexts like this, we think of as a very constructive kind of property. On the other hand, holding in wider contexts, not just in the closed context, it's actually a very anti-constructive property that having it in arbitrary contexts would be a definable global choice, a very strong non-constructive property. So can we look for any more in between? We can, and one thing we often do is what could be called the rule of countable choice, it's sometimes known as, which is the existence property in the context of a single variable of natural number type, saying that if whenever you've got some object with property depending on a natural number, and you can prove that for each natural number something exists, then again there should be a definable function on natural numbers picking out witnesses. And again, categorically this corresponds to projectivity, except now instead of saying that covers of the terminal object split, it's saying that covers of the natural numbers object in some classifying category split. So I'll be looking at results of this form, and especially for intuitionistic higher order logic. And so I should give a quick sketch of the history. I'll try and keep it very quick, and also explain the title a bit, which is that this is results which were proved first using proof-theoretic techniques by Hayashi and Friedman and Shedrov in the 70s for various systems, including close to I-hole or for I-hole, but that didn't quite get published. And also around that time, Freud had given a very beautiful, kind of very well-known, familiar to many people in the audience, I'm sure, proof of the existence property itself for higher order logic, analyzing the proof-theoretic proofs that had been given before in categorical terms, and an extremely clean analysis of it, showing how one of the kind of classic results of how categorical analyses of logic can really clarify things beautifully. And so I think quite a few people at that stage thought about how the proofs of the rule of countable choice could perhaps also be analyzed cleanly in categorical terms. And I believe that various people thought about this a fair bit, and Makkai presented his work on this and had an unpublished manuscript that was circulated at the time. And these went down, these results went down in print in the classic book by Lambeck and Scott on categorical logic in particular, naming these results and attributing them, but not including the proof, referring to those manuscripts for the proofs. And unfortunately, the categorical versions of the proof never did end up published at the time. The manuscripts are out there. And so a few years ago, when I and Henrik Rochelle originally were trying to find out about this and see if it was still out there anyway, because it sounded a very nice thing to learn, we met Makkai while he was visiting Stockholm and asked him, and he very kindly sent us a copy of the manuscript. And they're really lovely notes, and it's such a shame that they aren't out there. So we asked him if he was happy for us to write up some version of it so that it could try and get put on the record. And he said he was very happy for us to. So this, and Andrew Swan joined us for it. What I'm presenting now is kind of our attempt to give a version of this, a treatment of this, which of course, as ever, when one sort of starts writing up someone else's work, it ends up taking a new direction and slightly changing a bit. So this is not quite, I don't want to put any sort of mathematics into Makkai's mouth. This is both very much based on his treatment, but also any lapses in taste especially should be blamed on us. And of course, as we saw in the last talk, one must be very careful about giving credit when working on things that were kind of thought about a lot and known a lot in the past. So I should be very clear that lots of this is things that either are in the literature or that we've learned from folklore, and the rest, very probably, we're rediscovering things that other people have known and thought about in the past. But so we're not trying to sort of claim credit for this as new work so much as we hope that we're doing something useful. We hope that it will be useful and enjoyable for people to have this put out there in writing more publicly than it has been. So, all right. So before getting into the rule of countable choice, I'll warm up by quickly going over Freud's categorical proof of the existence property, which is, so it's showing that the terminal object of the free topos is projective. And the proof is that you first show, and this is a sort of routine calculation once you have the statement, that if you've got any left exact functor of toposes, then its comma category is again a topos, and one of the projection maps is illogical. And then you do that gluing construction with the global sections functor from the free topos to set. And now you use the universal property of the free topos to say, okay, so you can then get a section of that comma category, an interpretation map from the free topos into that comma category. What does that concretely look like now? Concretely give now on any epi into one, well, it has to take it to some epi in the comma category. You can characterize epis in the comma category as, I won't give the full characterization, but in particular, they imply that the left-hand side of the square that you get is itself epi. And now that exactly means that what that map to the comma category gave is an inhabited thing over one, and it maps into the global sections of A. So it shows that A had a global section, which is exactly what we needed for projectivity. So now, here is an outline of a proof of the rule of countable choice, phrased at a quite high level and in syntactic terms for now. And so at this level, this could equally well be a kind of sketch to lead into the categorical proof or into one of the proof theoretic proofs. That suppose we have an existence statement over the natural numbers that's provable in intuitionistic higher order logic. By compactness, it can only use finitely many iterations of power set. So it's, in other words, that's saying it's lying in some finite rank fragment. We look at the finite rank fragments, which are the fragments where you bound how many times you can apply the power set operator. But now syntax and proofs are all finite things that we can internalize into IHOL itself. So IHOL itself can see that this finite rank fragment proves this statement. We can specialize a bit to numerals and pull the natural number quantifier outside back into IHOL. And now the thing on the inside about the finite rank fragment That's the kind of thing that the plain existence property tells us about. And so by internalizing the proof of the existence property to I-hole, we can show that then I-hole now says, okay, for all n, there exists some witness to this statement that's provably a witness in the rank R fragment. But now, so this looks like we've come full circle to something very similar to what we started with. We've now got a for all natural numbers there exists something in I-hole. But now the existence isn't of an arbitrary kind of type of thing. The existence is of a term of some syntax. And syntax can be Gödel numbered. Syntax can be implemented with natural numbers, with sort of decidable proof checking so that you can look through all natural numbers, see if they code suitable witnesses, suitable proofs. And so by searching now, from knowing that there exists a witness, you can search and find it. So I-hole can definably give the witness. So because we've used the finite rank fragment to change the quantifier being syntactic, and that let us do the getting out of the existence into a specific choice for it. And now finally, to get that back into saying I-hole can see that the finite rank fragment has something witnessing this property, we need to pull that back into, so I-hole itself really sees as something witnessing that property. And for that, we need to know that you can have that within I-hole, you can interpret I-hole R into its standard model, into the ambient I-hole itself. And so now for the categorical proof, we'll follow this outline, but we need to change each step into something a bit categorical. So instead of starting with an existence statement, we start with a cover. Compactness, we'll want to use, instead of the finite rank fragments of the logic, we have a corresponding notion of a ranked topos, that it's like a topos, but it only lets you use the power set operator finitely often. We can internalize free structures. That corresponds to internalizing syntax. So we've got the free topos looking at the free R rank topos. Again, we specialize to numerals. That's just the same as it was before. Again, we can internalize inside the free topos or the slice over the natural numbers now, the fried gluing proof to show that internal projectivity holds. And again, then we want some sense in which we can say categorically that the free topos or its slices can see that the internal free finite rank toposes are Gödel numbered. And so that gives us this existence witness again. And again, we want to also be able to say that the free topos can see, in some sense, the standard model of the finite rank fragments. So this is the outline that we'll follow, and the rest of the it will be looking at essentially each of these steps in turn, building up the machinery to be able to come back to this and have a precise meaning to every step here, a precise idea of how we're doing each bit. So the kind of core notion that we're working with throughout is these finite rank fragments, where which we take to be sequences of regular categories of natural number objects and embeddings, preserving all that structure of length R, and such that at each stage in the sequence, you don't necessarily have power objects here, but the objects in here, they have power objects at the next stage. And so overall, starting from sort of the first stage, you have R many. Right, typo here, it should have been starting from 0, not 1, but you should have R many applications of the power object available. And the idea one can see this as is really that the last one is the total category, and that all the others are just subcategories representing predicates of having rank less than some amount, so that as long as your rank is below R, you can still apply the power object operator, but you count up the rank, and at some point you can't anymore. And the key technical point is that the free R toposes are just as nicely behaved as the free topos. In particular, you can arrange for them to be both strictly initial in a essentially algebraic one category. This is useful because it makes the internalization into other categories much easier, because the machinery of essentially algebraic theories is available to you for that. But on the other hand, it's also essential that they're bi-initial in a two category where the logical functors are not strict, since at the stage of the fried gluing, they're, no, sorry, not there actually, a later stage, the stage of the standard interpretation and checking its commutativity, one needs it to play well with natural isomorphisms and logical functors that aren't necessarily strict. Compactness is straightforward in this, that we can say that the free topos, we can show that it is the filtered colimit of the free R toposes, just by, I won't go through the details of that, but the free topos is, as one would hope, it's the colimit, which will let us apply compactness. The main tricky bit for the rest is that we need to handle internal and external categories together, and the standard toolkit we'll use for that is indexed categories, with three particular kinds often coming up. We can see categories with pullbacks as self-indexed. We can see internal categories as indexed over the category that they're in. And we can see any ordinary category as an indexed category over any category by its constant indexing. And almost everything we do with indexed categories will be a kind of work out with one of these three. And so the two of the main steps that we needed, the fried gluing and having the standard model available at the end, both of those, what they need is that you need, let's say the fried gluing, the classical standard presentation, it uses the whole category of sets, which is a large category. When you're trying to internalize it, the internal free R topos inside the free topos only has the universal property with respect to other internal ones. So other small ones from the point of view of the free topos, not to a large one like the whole free topos itself. So to use its universal property, we'll need to have other small, so other internal sub R toposes inside the free topos. And the technique that we'll use for constructing these is what, coming from type theory, I'm always inclined to call universes, which is just families of types, object sets that are closed under the type forming operations. So in the topos theoretic extensional type theory context, of course, those families of objects are just a map seen as the family of its fibers, and saying that we say what it means for them to be closed under power objects, finite products, and so on in the obvious ways. And so whenever you've got a family in a topos, or more generally locally Cartesian, in a locally Cartesian closed category, you can form the full internal subcategory on that family. It's like just saying you've got some family of sets, form the category of sets on those with all functions. If your family of objects was closed under suitable operations, then it will be a topos. Or if you had a sequence of families where each one was closed under finite products and subsets and things, and each one had power objects in the next one in the sequence, that will exactly then give you something looking like an R topos. And so the crucial step for building these is that what we know we can't be able to do by incompleteness theorems is that we know we wouldn't be able to build a inside the free topos or an arbitrary topos. What we can't hope to build is a family that is really closed under everything, including power objects, because that would show its own consistency. But what we can hope for is something modeling the finite rank fragment, a sequence where each one has power objects for the next up to a finite length, and we're closed under enough of the other operations to get an R topos. And this we can do with just a bit of sort of type theoretic work, essentially. And so what this lets us get is that given any basic family, you can include it inside a full internal subtopos in any topos. And this is what corresponds to the proof theoretic, to the reflection that's used in the proof theoretic proofs. And so this lets us internalize fried gluing in a way that looks very similar to before, almost exactly the same, except now instead of using actual sets or the ambient category, we have to go via a small internal subcategory. But all of the rest works just as it did before. And on the other hand, the standard model, again, we can express nicely what the standard model should be using indexed categories. It should be, we've got some arbitrary topos E, and inside it we've got the internal free R topos. So we've got an internal category here, and then the ambient category it's living in there. They live in the same world by seeing them both as E-indexed categories and both E-indexed R toposes. And so we can what we can want is a logical functor between them. That's what the standard model should be. A sort of map from the free R topos into sets that preserves all the logical structure. And once we have these small internal sub-R toposes that contain enough, we can do that. And also, just again, by directly checking the universal property, we can see that if we compare that with the interpretation of the external, the actual free R topos, it commutes. So we can take syntax, internalize it, and then do the internal standard interpretation into E. Or we could have just directly interpreted it to E. Those agree. This all comes very kind of directly from their universal properties. And so finally, the last step we had to explicate was Gödel numbering of syntax. This we can give a bit of a categorical analysis of by seeing the kind of category that suffices to construct essentially algebraic syntax, or one of the nice analyses of it that I think Maietti first presented this one as good for it, was list arithmetic pretoposes. They're what suffices to give initial models, and their functors preserve initial models of finite essentially algebraic theories. And in any list arithmetic pretopos, you can look at the enumerably presented objects, which are the objects that look roughly like what it was about syntax that we used when we talked about Gödel numbering. It's that they're a decidable subset of the natural numbers, quotiented by some equivalence relation that itself is enumerable from a decidable subset of the natural. I am wrapping up in just a moment, Ed. And I hope, since we started a couple of minutes late, I hope, excuse my pushing a little. Right, and so over any list arithmetic pretopos, the enumerably presented objects themselves form another one, and their realization into the original one is, again, preserves all that structure. And so initial models of essentially algebraic theories factor through these enumerably presented objects. And just by exactly the same way that Gödel numbering did, those allow us to convert existence properties into chosen witnesses. And so now we can come back to the original outline of the proof and see that every step we had of the original proof, we've given a categorical sort of explication of what's involved in the step. And yes, so yes, I will wrap up since I'm a little over. But this has taken the original outline and seen that one can again see it all in categorical terms. So again, the language of toposes for I-hole giving a very nice analysis of something proof theoretically, which avoids some of the gory details. Thank you very much.
Okay. Okay, we have time for one or two questions. Hello, thank you very much for your very interesting talk. I was wondering whether any fibration would split, or rather what kind of condition on the fibration representing a term in fab theory would you expect it to split in this sense?
Right, so I think the sort of general question in that direction, I think the most investigation I know of, that kind of Martin Escado has some lovely investigations in these directions of searchable types is the phrase he uses for those. And he and some collaborators have looked a fair bit at those. I think the techniques that we're using here, I think, don't give so much more general answers beyond using it over the natural numbers. But at the same time, what our kind of way of looking at it and the countably presented sets is, I think, informed a lot by the searchability kind of viewpoint of Martin Escado and his co-authors on there.
Okay, thank you. Okay, I see that there are two questions online. Let's begin with Steve. Steve, please.
Yep, I have to unmute. Thanks, Peter. That was nice. It looks like the techniques in this proof can be used for other things too. I wonder if you've thought about doing other things like the Gödel incompleteness or the second incompleteness theorem. it looks like you're kind of in the neighborhood of those things too.
Right, yes. So I think, yes, some of these are definitely in the neighborhood of those. Not in, I think, again, not in sort of awfully new ways. It's kind of going in the direction of the arithmetic universe's approach to those that have been, again, thought about by quite a lot of people, but that, right, some of these were sort of slightly different ways of phrasing them that we have.
Yeah, it would be nice to have a proof of incompleteness in elementary topos theory, rather than having to develop all the arithmetic universe machinery. So I think that would be worthwhile. Thanks for the talk.
Okay, and then finally, Paul.
Thanks. I disagree with Steve there. I think arithmetic universe is a great things that need more attention than they've been given. But my point to Peter was when I was thinking about these things, certainly not in the detail that you have, I thought, how could this bluing result possibly work unless we were relying on the axiom of replacement in the category of sets? Am I right or wrong in thinking that? Since you
Right, yes. Right, I always find that any question about replacement being necessary difficult to understand, because somehow what it feels to me somehow is that set theoretic foundations, they have other things left out that they need replacement to provide, but that sort of replacement, the role of replacement is more completing other things that are missing than quite that it's wanted itself. But right, it's what gives the induction into the large category directly. And so here we had to have passed to the finite rank fragment so that we could construct a small category that models the thing we needed.
I was wondering how that managed to be necessary, but I will trust your word on that.
I mean, I guess that's where the induction into the small category is what doesn't need replacement. Induction into the large category is where I would see the replacement is needed.
Exactly. Yes.
Yeah, extending, and so by avoiding doing the large category, by getting into the fragment where we have small models, that's how we're able to sort of just duck under the bar and avoid needing replacement.
My thought was that it's depends. It's the recursion over the entirety of the free whatever it is that you're using, the free topos or whatever, that should require replacement. Is that reasonable? Agree with that, or
I just think of it as being recursion into the entire one, not recursion over the entire ambient free topos. If I'm understanding you right.
We should have a private discussion.
Yes,
Okay.
yes, we probably shouldn't cut into the next talk.
Okay, I think we have to conclude here. Thank you very much.
Thank you very much.
Thanks, Peter, again. And then we have a break of 1 minute.